Hello, AP Stats. This is our first video. I plan on making one of these for each chapter that's left. And so this is 22, and we've got 23, 24, 25, 26, 27. 6 chapters. We are going to cover chapter 26 and 27. But the AP test only goes through chapter 25, but most of you have expressed wanting Mount Hood credit, so we're going to do 26 and 27 too. And I'm going to make one video per chapter, and we're going to do a hypothesis test, a confidence interval, one of each, and that's that. And it's going to be pretty quick, and you are going to be reading each chapter, preferably before you watch the video, but you're going to have to read it. And then I'm going to give you some odds that I think are good for you to do. But, you know, have the bookmark in the back, read the question, look at the odd, and work through it, check it. And then I'm also going to have FRQs with their answer keys for each chapter in the Google Classroom. So a link to the video, FRQs, odds from the book you could do. You're going to read the book. And then your homework will be through Albert. And I don't know quite exactly what that's going to look like yet with the grading. They haven't told us yet. But by Monday the 13th, we should know what that's going to look like. And what the class will look like in terms of like how we'll meet. That's still kind of getting worked out too, because Zoom is no more. We are not allowed to use Zoom. So we'll see what's going on there. But for this video, let's talk about chapter 22, which we had started and we were halfway through. We did the confidence interval. So here is the list. Keep this list going. Can we see that? Sorry, I don't have an iPad Pro and my document camera is an older model, so it's going to be holding things up, but we've got it. We'll make do. We did the 2 proportion Z interval, and I think we still have to do a 2 proportion Z test. Why don't we do a 2 proportion Z interval from the book just to get us back into it? So have your book out, okay, and turn to page 520, and we'll do number 13 on page 520, ear infections. All right, here we go. A new vaccine was recently tested to see if it could prevent the painful and recurrent ear infections that many infants suffer from. The Lancet, a medical journal, reported a study in which babies about a year old were randomly divided into 2 groups. Okay, so this is an experiment problem. They're randomly dividing them. One group receives the vaccination, the other does not. So we're not just taking random samples from populations, so that'll affect our conditions. During the following year, only 333 of the 2,455 vaccinated children had ear infections. Let's write that down. That's like our sample proportion for vaccinated is 333 out of 2,455. And you guys are writing this out with your book open, or else these videos will not work. And then the unvaccinated, the proportion of unvaccinated that got ear infections was 499 out of 2,452. And let's crunch those out. 333 out of 2,455. 0.1356 and 0.2035. All right, so here's what I've got down. I've got my proportion of vaccinated that got an ear infection, 13.56%, and the proportion of the unvaccinated that got the ear infection, 20.35%. So it looks like there is a difference, right? That's what we want to know. And how big is the difference? And in our sample, in this experiment, the difference is about 7%, which is pretty big. And the sample sizes are also pretty big. So I'm guessing that our confidence interval will show that there is a difference, that the vaccination did prevent ear infections. There is a significant difference. And we are going to make a confidence interval, a 2 proportion Z interval. Name it. And then it's always, and you're also going to want to give the difference. What is the difference that we found? And I like to always do the positive or the higher number minus the lower one to keep the difference positive. So the unvaccinated minus the vaccinated, 0.2035 minus 0.1356 is 0.0679. So about a 7% difference is what we found. And is that the true difference? Probably not, but hopefully it's close. Okay, so we are going to capture the true difference, or try to, in a confidence interval. So we're going to go from that 0.0679 and reach out. We're going to make a 95% confidence interval, so we're going to reach out 1.96 standard deviations from that point estimate, that 0.0679, the difference that we got from this experiment, and that'll be that. And then we need to check our conditions. Okay, for the sake of time, I might not write it all out, but I might just say it, okay? So random. Now, we're not drawing from a population. We had infants, and we randomly put them into treatment groups. So that's where that takes place, and that's good. That's necessary. So that's what you could say for the random condition. The infants were randomly put into treatment groups. 10% doesn't really apply in this situation because it's an experiment. You're not going to have, 2,455 vaccinated children or 10% of all vaccinated children, but it's an experiment. So that doesn't apply here. Okay, the success failure condition. This we need to check, and we need to check it for both samples. So we'll do that really quick here. So we have 333. So you could just do 2,455 minus 333, 2,122. And yes, there are definitely more than 10, but you still need to write it out. You still need to show that there are more than 10 on the AP test. Okay, so I'm giving it a check. And I'm saying there are more than 10 successes and failures in both groups. So you're going to have 4 numbers there instead of 2. You have to check success failure for both samples. You also have to do the 10% condition. If this was a sampling from a population, you would check the 10% condition for both. And then the last condition is the independent groups condition. This is a new one. The groups must be independent of each other. Most of the time you'll just say the 2 groups and use context. So the people below 40 and the people above 40 are independent of each other. Check, done. And that's pretty much what you'll do. So here you'll say the unvaccinated infants and the vaccinated infants are independent of each other. Check. And they were randomly put into groups. So, and we have no reason to see that they are related. It's not like siblings or something like that. So independent groups, check. The infants who are vaccinated and the infants who are unvaccinated are independent of each other. So check, 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 all conditions met. All right, so now we're going to make the interval. And we're going to do it on our calculator because that's how you're going to do it in the AP test. I'm going to write it out quick too, using the formula because you got to understand the formula. But let's do it on our calculator. So we go to stat, tests, stat over to test, down to the 2 proportion z interval. There we go. I did the unvaccinated first. So for my X1, N1, I'm putting 499 and 2452. And then minus the vaccinated, 333 out of 2455. And it does want a 95% confidence interval. So that is what I'm entering in. Enter. Boom. And there is our confidence interval. And that's all you need on the AP test on a free response. 0.04695 to 0.08878. There you go. And then interpret the interval. We are 95% confident that, okay, now we've shown that there is a difference because it goes from 6.9% to 8.9%. So you could say it like this. You could say it like we are 95% confident that the true difference between the proportion of babies that get ear infections who are unvaccinated and the proportion of babies who get the ear infection who are vaccinated, and then maybe do parentheses, unvaccinated minus vaccinated, is between 0.0695 and 0.08878. So you could say that the true difference is between that and that. Now you could also say it like this. We are 95% confident that between 0.0695 and 0.00878 more infants get ear infections who are unvaccinated. So we are 95% confident that between 0.0695, or you could say that between 6.95% and, I have an extra zero there, sorry. We are 95% confident that between 6.95% and 8.78% more infants get ear infections who are unvaccinated. And that's, a nice way to say that, yes, if you're unvaccinated, there's a, 7 to 9-ish% chance, higher chance that you'll get an ear infection, is what you would say. All right, there you are, okay? Now, you still need to know the bare bones of that thing, right? Which is the point estimate, the sample difference, which is our 0.0679, plus or minus the margin of error. So we're going from that 6.79% difference, and we're reaching out. How far are we reaching out? Well, we're 95% confident. So it's a z-score. We're reaching out 1.96 standard deviations. Okay, what's the standard deviation? And that is on your formula sheet, which you're going to have right in front of you. And that's like the P1Q1 over N plus, yep, you guys can, I'm going to write that down right here. So this guy is the equation. Okay. And that's our 6.79%. That's 1.96, our critical value, point estimate, critical value, and that's our standard error, our standard deviation, our estimation of it, of the sampling distribution. And you could plug in everything in there and you would get the standard deviation, but you don't have to do that, okay? Okay, great. So let's do a hypothesis test now. And why don't we do number I have a number to do, but we could really choose any of these from the book. Okay, well, let's do, so the chapter 22 starts out with the confidence intervals and the problem set, that ends with the hypothesis test, and you want to do both. The odds are great because you have them right there. You just flip back and forth to check how you're doing it. Let's do 24. 24 on page 521. And now we're doing a hypothesis test. So it's still a two proportion problem. You're still comparing two proportions. You want to know, is there a difference between the two proportions? And remember, for a confidence interval, it's all about if zero's in the interval. And if it is, then you can't conclude there's a difference. This one did not have 0 in it, so we did conclude there was a difference. Now, for a hypothesis test, you always assume that there is no difference. They are the same. That's the null. That's the assumption. So let's run through that. Let's run through a hypothesis test, and then we'll be done with our chapter 22 video. Okay, so we're on number 24. It says a survey of 430 randomly chosen adults found that 21% of the 222 men and 18% of the 208 women had purchased books online. Okay, so let's write those out. 21% of the 222 men. So the sample proportion of men, it's out of 222, and we know that it was 21% of those. So I'll crunch out that sample proportion, and you're going to want that when you put it into your calculator. You're going to want the sample proportion. So I got 46.62. I'm going to round that up to 47, round that correctly there. So 47 out of the 222 men had bought books online, and then the sample proportion for women is 18% of 208 women. So 208 times 0.18, 18% of them is about 37.44. So we'll round that down to 37. Okay, so those are the two sample proportions of men and women who buy books online. Keep reading the question. So A, is there evidence that men are more likely than women to make online purchases of books? Okay, so let's crunch out those sample proportions and just see what we got from our data. I got 0.212, 21.2% of men bought books online, and 0.178 for women. So it does look like more men bought books online, and let's get that sample difference. You want to write that down. And I'm going to do men minus women to keep it positive. And I got a sample difference of 0.034. Okay. And then the question is that because more men actually buy books online, or is that just due to sampling variability? And you can take another sample and the results might be totally different. So how do we figure that out? We are going to do a 2 proportion z-test, not a 1 proportion, 2 proportion z-test. Name it is what they want. Got to name it. And then we are going to write our hypotheses. Okay, and the null is always no difference. There's no difference between the proportion of books men buy, women buy online, it's just the same for both of them. Doesn't matter if you're a man or a woman. It would be the same. So the proportion of men who buy books online equals the proportion of women who buy books online. And note how I didn't use p hats on my hypotheses, because the hypotheses is like the make-believe reality, but we're saying that this is actually that they're actually the same, in our null reality. And then the alternative, it does say, is there evidence that men are more likely? Men are more likely. So for the alternative, we're going to say the proportion of men is greater than the proportion of women. And then we also have to define those. Let me do that really quick. P is the proportion of men who buy books online. Okay. And then PW is the proportion of women who buy books online. And I'm not going to have great handwriting here, but I'm going to read it to you so you'll be okay. So here's how you write your hypotheses. You want to make sure you use context. So the proportion PM, the proportion of men who buy books online, the proportion of women who buy books online. The null is that they're the same, no difference. And the alternative is that more men buy books online. So the proportion of men is greater. Okay. Let's check our conditions. This one is a sampling from a population one, so it should be pretty straightforward. Random, a random sample. So check, problem states it was random. 10%, okay, so 222 men and 208 women, and it's just adults. So yeah, that's fine. You could say 222 men are less than 10% of all men, and 208 women are less than 10% of all women. Check, check. Okay. All right, success, failure. So got to check them for both. So for NP for men is 47, and Q 222 minus 47, 175. And then check your success failures for the women. 37 have bought books online, so the NQ of that would be 208 minus 37, 171. Okay, got to check them for both. There are more than 10 successes and failures for both men and women. And then independent groups, here's what I'm going to say for that. The men and women are both independent of each other. Check is fine, because it's pretty straightforward. All right. I didn't write all those down just for the sake of time, but I said them. So you guys can pause it if you want to write those down. So independent groups, we have the men in the study and the women in the study are independent of each other. Check. It doesn't say they were like husband and wives or anything like that. Okay, all conditions met. Great. Let's do the test. Now I'm going to do it on the calculator again, just because that's all the work you have to show in the AP test. But I am going to show the drawn out sampling distribution, the shaded part, the p-value part, the z-score, how you get that. You don't have to draw out the sampling distribution on the AP test. I made you do that, but that's actually not required. Let's do the bare bones right now, and then we're going to draw out the sampling distribution anyways, just to get a complete picture of what's going on. Okay, so you name it, you write your hypotheses, you check the conditions, Now you do the test, which we can do on the calculator. So we're going to do a 2 proportion z-test, hit the stat button, go to test, and go to 2 prop z-test, enter. Okay, now the order of these, I did men minus women. So I'll put the men first, 47 out of 222, and then 37 out of 208. Note when you're putting them into the calculator, the problem says 21% of 222 men, and sometimes people just put that in. The 21% of 222 men, they do 222 times 0.21, like that, and they get a decimal up there, and they go to calculate, and it gives them an error message. So make sure you always round that 46.62 up to 47. Because those have to be a sample proportion. You can't have a decimal. Those are sample proportions you're putting in there. And then we want greater than. Okay, so there we go. Throw that in, hit calculate. Bam. Okay, what do they need from you? They need 2 things. All they need is the critical value, which is the z-score, which is 0.88416, I'll say. And they need the p-value, which is 0.188. Those are the 2 things they need. They always need the critical value along with the p-value. So you could even just write it like this. Just kind of write it like that's the critical, that's the z-score, that's the p-value. Okay, and then we would interpret the p-value, which is 0.188, which is a pretty high p-value, especially the 5% alpha. And you could throw that in there. I'll throw that in there. This problem doesn't specify an alpha level. So I'll say using alpha equals 0.05 with a p-value so high we fail to reject the null, there is not sufficient evidence of the alternative. There is not sufficient evidence, and I'll steal their language again. There is not sufficient evidence that men are more likely than women to make online purchases of books. To make online purchases of books. You could have said that shorter, but I just copied them. Okay, using alpha equals 0.05 with the p-value so high, we fail to reject the null. There's not sufficient evidence that men are more likely than women to buy books online. And there you go. That is a 2 proportion z-test. Okay. Now, okay, so the drawing the sampling distribution out is actually a little bit of work. So how about this? Those of you who are good, you can do it on their calculator. Now, the trick with drawing out the sampling distribution is that when you make the standard deviation, you have to pool the 2 sample proportions into so they're the same, because the null is that they're the same. So that's what makes that tricky. And I do want to run through that. But again, you're just going to do it on your calculator. You might get a multiple choice about this. And it's good to know just about overall what are you doing. You're assuming the null is true. You're make-believing that there's no difference. So if there's no difference, what's the probability that we would have gotten the difference of that 0.034, that 3.4%, if there was no difference? pretending that they're the same. What's the probability that we would have got this 3.4% difference? Well, it's an 18.8% chance that that would have just been due to random sampling variability. And that's pretty likely, actually, then, of getting that difference. So we did not conclude that men bought more books, right? That's the idea. And then then you take it even further with drawing the sampling distribution. So if you're good to go, feel free to do some odds. And I wrote this down. I wrote 1 through 25 odd. I don't expect you to do all those, but they go quick if you have the answers in the back, just checking it. But the front half of the assignment is confidence intervals. The back half of those are hypothesis tests. You want to do like a few of each. And then I'm going to get the Albert assignment for you on Monday. All right, so get going on those. Look at the FRQs. But for you high flyers who really want to understand what's going on, because it's good stuff, let's quick run through the sampling distribution. Okay, so here we go. We assume the null is true. So I'm making a sampling distribution, normally distributed. What's the null? The null is that they're equal. They're the same. The null is that there's no difference. So the null is that the mean of the sampling distribution is 0. There's no difference, actually. That's our pretend null, right? Well, what's the standard deviation? And then on your formula sheet, it's got this formula, and pretty much these are the two, right? These are the two sample proportions. They're different, but we're living into the pretend theoretical situation where they're the same. So we need to make those the same. So we take the 47 and the 37 and we pool them together. 47 and 37 is 84. And then the denominators we pool together, 222 and 208 is 430. So out of the total 430 people, men and women together, 84 bought books online. That's both pooled together, okay? And they're all mixed up, men and women, and there are more men, 222 than 208. So it's like, not a perfectly even split, but that's just them pooled together. So pooled together, 84 out of 430 is a 0.1953. 0.195. So 19.5%. So we're going to pretend that it's just 19.5% bought books online for men and women. For both of them, it's 19.5%. No difference. And that's what we're going to use for our no difference. Now, is that actually true? No, probably not. But we're just pretending that for this hypothesis test. It's 19.5%. So that's what we use in the standard deviation formula. We use that 0.195 for both samples. So I'm crunching out that standard deviation formula now. You guys feel free to do that. And I'm running out of room, so actually I'm going to rewrite this so it's clearer. Bear with me. All right. And I got to crunch it out to a number now. You guys are doing this too, I hope. Okay, hope I did this right. I got a standard deviation of 0.00146. I'll say. Okay, there you go. That's my pooled proportions. You said the 222 and the 208 for the men and women, but we're just saying the 222 men, it's 19.5% bought books online. The 208 women, it's 19.5 books. It's the same for both samples. All right, so 0.001462. It seems really small, actually. Too small. Hold on. All right, what did I do wrong? Did I forget to square root it? Oh man, no, just leave it. Okay, I think I forgot to square root it. Yeah, that's true. All right. I forgot to square root it, and I got it out of my calculator. So my answer might be a little off because I rounded a little bit. Okay, so after you square root it, sorry about that, it's 0.038236, and I might have rounded that a little bad, but I don't want to type it all back in, but forgot to square root it. But I saw that I made the error, especially from what we got in our calculator. Okay, so let's find the z-score now. All right. All right, I'm gonna put in my 1, 2 standard deviations really quick, just because they look so nice on the normal model. But I'll only do it on the positive side. Oh man. Okay, 0.077647. All right, so we got it 0.034. 0.034. Okay, so there's my sampling distribution. 0.038, so it looks like we're a little under one standard deviation. We're going to find the z-score there. 0.034 minus 0.038 divided by that 0.038236 standard deviation of our sampling distribution. Oh, I actually wrote that wrong. It's late, people. It's after 11. 0.034 minus 0 value minus the mean divided by the standard deviation, getting the z-score. All right, there's my z-score, 0.8892. Okay, and it's a little different than what we got in the calculator, 0.88416, but that's probably because I rounded off. Okay, but almost one standard deviation, looks right. Okay, and we're shading above that. So normal CDF, up lower bound that 0.8892, upper bound 99. Normal CDF 0.8892 to 99 is 0.187. I'll kind of circle what I just put in. 0.187 there. Okay, and we got 0.188 above there on our calculator. So that's the extra work that you don't have to do. Drawing out the sampling distribution, finding the standard deviation, which is, can make little mistakes, as we've seen. So, okay, that's chapter 22. How many stayed for that last part? Probably only a few of you. And then we'll be discussing this, and I'll be answering your questions, and we're going to figure out all how to do that. You guys will hear more about that. All right. Thanks, guys.